Hi there, during this session I'm going to be talking about circular motion. Before we start the details of circular motion though, I just want to clarify that we're often going to have to use radians as a measurement of angle. So let's make sure we've all got degrees and radians and our understanding between them clear amongst ourselves before we move on. So, a radian is defined then as arc length divided by radius of a circle. So this is the arc length. And then we have the radius. Now, radian is dimensionless because if we think the arc length and the radius are both going to be measured or have a unit of meters. So meters divided by meters means we have a ratio and no units. So that's why radian is dimensionless. If we look how this pans out, it's quite useful here. You see we're starting at 0 degrees and 0 radians are equal. If I now rotate to 180 degrees, thankfully shows that 180 degrees is equal to pi radians. So that means 90 degrees is equal to pi divided by 2 radians, and 270 degrees is equal to 3 divided by 2 radians. And when we complete one full rotation of 360 degrees, that is equal to 2 pi radians. A couple of questions here just to see if you've got that conversion done. Can you convert these angles into radians? Pause for a moment. Let's see if you can do those. And hopefully you've come up with these solutions. And vice versa. Can you convert these angles into degrees? Pause for a moment. And hopefully you've come up with these solutions. If you're having any problems with these, just go back and check your understanding, because it's really important you get this right as we move forward. So now let's talk about circular motion in a little bit more detail. Start off with, I'm going to describe something called angular velocity. Now angular velocity, just like normal velocity, stems from displacement. And this is starting off with angular displacement. Angular displacement is how far something has rotated in radians, whilst angular velocity tells us how far something is rotated in radians per second. So it's how fast something is rotating. Let's apply this to a problem. Bonnie sits on the outer rim of a merry-go-round and Clyde sits midway between the centre and the rim. The merry-go-round makes one complete revolution every 2 seconds. Clyde's angular velocity is A, the same as Bonnie's, B, twice as Bonnie's, C, half as Bonnie's. Well, in this case, the amount of angles of the angular displacement is identical for Clyde and Bonnie. So therefore, Clyde's angular velocity is the same as Bonnie's. Let's extend this problem now. Same situation, but now we're thinking about Clyde's speed. Okay, remember, speed is distance travelled divided by time. Now in this case, if we look at the arc length for both of these situations, we're going to see that the arc length travelled by Bonnie is going to be much greater than that of Clyde. So therefore, Clyde's speed is going to be slower than Bonnie's. So recognise that speed is going to be slower in this situation, thinking back to our understanding of what speed relates to. So let's link up velocity and angular velocity. Okay, there is a relationship here. If we think, we know that angular in radians is defined as the angle is the arc length divided by the radius. Now if we rearrange this, we can recognize the arc length is the radius multiplied by the angle in radians. Velocity is going to be the arc length divided by time, so therefore radius times the angle in radians divided by time is equal to the velocity. And this all comes out very simply as velocity in meters is equal to the radius multiplied by the angular velocity. Let's apply this to a problem. A spin dryer whirls cloves at an angular speed of 85 radians per second. The drum has a radius of 0.2 meters. Calculate the speed of the cloves. Using that formula gives us 17 meters per second. Moving with constant speed but accelerating. That doesn't seem to make sense, but it does do when we're thinking about something travelling at constant circular motion. The constant circular motion means that the distance travelled divided by the time it takes is always going to be the same. So therefore, the speed and actually the magnitude of the velocity are always going to be the same. But what happens here, if we look at the diagram, we can see that from velocity 1 to velocity 2, there's a change in direction. Now that change in direction means that there is an acceleration. Remember that changing velocity doesn't just mean magnitude, it can also be direction. So we have an acceleration. And we can see wherever we go around the circle, the acceleration is towards the center of the circle. So if anything's traveling in a circular motion, it's actually accelerating towards the center, even though it will have constant speed. Going a little bit further than that, the statement we're going to look for, uniform circular motion, the speed is constant but the velocity is changing, and therefore acceleration is a change in velocity. That's the statement we need to make sure is clear. Towards the center of the circle, that means if we look at the expression for centripetal acceleration is v squared divided by r, the radius. We can break this down if we think about v is the velocity at an instant in time, i.e. the constant speed. R is the radius of the circle. I've expanded this, so if we think about v squared, this is going to be the circumference of the circle divided by the period. So therefore I can calculate it in a slightly different way. Acceleration equals 4 pi squared times by r divided by t squared, which is the period of one complete circle. Now, if it's accelerating towards the center of the circle, it means there must be a force being applied to the center of the circle. In all situations where something is rotating in a circular manner, then there has to be a centripetal force. Now that force is what maintains this circular motion. So if we think about, we know the centripetal acceleration, Newton's second law still applies, so force equals mass times acceleration. So this force is going to be equal to the mass of the object multiplied by v squared divided by r, which is the centripetal force calculation. Now this force calculation is really, really useful. We can apply it to some situations now. A car of mass 80 kilograms moves in a circular radius of 30 meters at a speed of 8.0 meters per second. Can you calculate its centripetal acceleration and the centripetal force acting on it? So here we're going to recognize that. Acceleration is v squared divided by r, gives me 2.1 meters per second squared. And the centripetal force acting on it here is going to be force equals mass times acceleration. So it's going to be 800 times 2.1, which gives me 1,700 newtons. The last thing I'm going to talk about is centrifugal forces. Now this is a misnomer, a scientific misconception, and I'll explain where it comes from. People often think that as they go around a circle that there's a force causing it to be thrown out. It's actually the non-existence of a force. What I mean by that is, we will understand that Newton's first law of motion means that an object will carry on in a straight ahead as long as no force is applied to it. Now, if you are in a car, the friction between the car and the road is going to cause the centripetal force. And that's a force towards the center of the circle. But what you're going to be undergoing is Newton's first law is going to expect you to keep on traveling in a straight line. So that means that unless there's a force of friction causing you to have that centripetal motion as well, you're likely to slide out because of Newton's first law wanting for you to carry on in the same direction. But if we break down the forces, this is just because of a lack of force between you and the car. So there's a lack of friction there. If there was adequate friction, then there'd be a centripetal force acting on it. So remember, this centrifugal idea, the idea there being a force causing you to be thrown outwards, is completely fictional. It is a misconception in science. Hopefully that covers everything you need to know about circular motion.